What's up, team? Today we're talking more about slope. You'll see the learning target above. It's a hefty one. It says I can show that a linear function has a constant rate of change. I can understand when the slope of a line is positive, negative, zero, or undefined, and I can identify if a function has that constant rate of change. We're going to discuss all that here. Then a few tips. Linear functions always have a constant rate of change. Please write that down. Please capture that in your notebook. That is a huge, big deal. And then I reworded that by saying if a line is straight, then the rate of change is always the same. All right, I want to discuss 4 different types of slopes. If I'm you, I would capture this in your notebook. The first one, I'll talk about a positive slope. Positive slope is one that when you read it from left to right, it goes up. It's like you're climbing up a mountain. So an example of a positive slope would be something like this red line. That is positive. Anything, any sort of positive slope. As long as it's going up, it's positive. On the other side, if it's going down, well, we call that a negative slope. It's moving down as you read it from left to right. A zero slope you'll run into every so often. A zero slope is one that is perfectly horizontal. It does not go up and it does not go down. Think of the floor that you're sitting on or that you're at right now. It's more than likely it's got a zero slope. So zero slopes are perfectly horizontal. The last one we're going to examine is what we call an undefined slope. That is a perfectly vertical line. For the time being, don't worry too much about why we call it undefined. We will we'll explain that in a future lesson. Okay, we're going to run through a few examples now. This is a table of data here. I'm telling you that this data represents a function, and it's our task to determine if there's a constant rate of change. Meaning, if we were to graph this, would it be a perfectly straight line, whether positive slope, negative slope, or even a zero slope or undefined slope? So we're here to check that out. Now, fortunately for this one's really easy to check. We can tell because the x values, they go up by 1 every time. And I'm going to write that in, actually. So to go from 5 to 6, we add 1. To go from 6 to 7, we add 1. And to go from 7 to 8, we also add 1. That's one way to check really quick if we have a constant rate of change. Now, that alone doesn't tell us that we have a constant rate of change. And we also need to check the y values. So if the y values are also constant, boom, constant rate of change, game over. So let's check. To go from 11 to 18, well, we have to add 7. And to go from 18 to 25, we also add 7. And to go from 25 to 32, we also add 7. So now we can definitely determine that we have a constant rate of change. And if you aren't convinced by this little trick here, you can absolutely use the slope formula, delta y over delta x. So when we do that, delta x, we would just take the greater y value, in this case 32, minus the next y value, 25, over, and that's going to be 8 minus 7. When we do that, we end up getting 7 over 1, and we could do that for all of these points and find that the constant rate of change is 7, but we basically already did that right here. So this particular table here, the data here, is a function with a constant rate of change. Here's the second example. Different table, different data. So again, on the x's, we see that these all go up by 1. To go from 7 to 8, we add 1. To go from 8 to 9, we add 1. And to go from 9 to 10, we also add 1. Sweet. This is going to be a fairly easy task for us. We now need to determine if the y values all go up by the same amount as well, either up or down by the same amount. So to go from negative 3 to 0, we're going to have to add 3. To go from 0 to 4, we're going to have to add 4. Yikes. Okay, we already don't have a constant rate of change. Sometimes we add 3, sometimes we add 4, but we only added 1 both times on the x-axis. So remember, the rate of change is how much does the y grow or not grow, or shrink, I suppose. How much does it increase or decrease when the x value grows by exactly 1. In this case, sometimes it grows by 3, sometimes it grows by 4. It can still be a function. That's okay. It can still be a function, but this is not a function with a constant rate of change. So this one we absolutely classify and say that it is not a constant rate of change. Again, we can still graph this. It's still a function. It's still good. It's still valid. But what's going to happen is when you graph it, it's not going to be a perfectly straight line. It's going to either have some like kinks in it and go steeper than not steep and so on, or it's going to have gaps in it or something like that. So still good, still fine, still a function, but not a constant rate of change. Okay, here's our last one. This one's going to be the trickiest one out of all of them. So first, let's look at the x's. This one's not as simple. They don't just go up by 1, but let's examine how much they do go up by. So we go from -1 to +1. We need to add 2. There's a difference of 2 between those two x coordinates. To go from 1 to 4, we're going to have to add 3. And to go from 4 to 7, we're also going to have to add 3. Okay, the hope isn't lost. This doesn't mean that it's not a constant rate of change. It just means we're going to have to work a little harder to check. So let's do the same thing with the y's and see what we can see. To go from 4 to 6, we're going to add 2. To go from 6 to 9, we add 3. And to go from 9 to 12, we also add 3. Oh, okay. So check this out. I'm noticing some patterns. To go from the first point to the second, we add 2, and then we add 3, and then we add 3 to both sides. That seems like good news. So what we would do here, if we were to do the whole thing kind of long-handed, we would do delta y over delta x for all 4 of these points. And I do that in my notes. If you want to check that out, feel free. But what we can also do is we could recognize that we've already done delta y over delta x for all of these points. We know that delta y means how much does the y change? And we've noted right here, it changes 3. To go from 9 to 12, it's 3. So our delta y for these bottom 2 points here is 3, and the delta x is also 3, because this changed 3, it went up 3. Okay, so this is telling us that we have a rate of change of 1 between these 2 points. If we follow that same pattern, it's really just a matter of putting 3 over 3 and then 2 over 2 and recognizing that all of those values are exactly the same. They're all 1. So this set of data here, this function, also has a constant rate of change. If we were to plot it on the Cartesian plane, connect the dots, it would be a perfectly straight line. It would happen to have a slope of 1. Okay, ask me any questions if you have them. Knock out this assignment. I believe in you.